This video is the second part of a two-video series on quantum brute force algorithms for finding passwords. The link to the first video is in the description. It describes what I mean by a brute force algorithm, introduces quantum computers, and talks about some quantum algorithms. Another preferred prerequisite for this video is the series on Markov's theorem that talks about a famous polynomial that I called the Chev, which has very useful properties. The link to that is in the description as well. I'll start with the current video now. We start this video in the realm of mathematical possibilities. In this realm, you'll see statements that we don't know to be true and we don't know to be false, like the Riemann hypothesis. You'll see mathematical objects that we don't know exist, but we don't know to be impossible either, like a never-ending game of beggar my neighbor. But one of the most fascinating aspects of this realm is not the inhabitants themselves, but the pacts they make. Take this statement that says that the gap between two consecutive primes can never be much larger than the square root of the primes. It has a pact with the Riemann hypothesis. Should the Riemann hypothesis ascend to the world of mathematical reality, it will bring the statement about primes along with it. With such promises, the Riemann hypothesis builds a large kingdom and gains importance in the realm. The Riemann hypothesis will either ascend with its whole kingdom or never ascend at all. Similarly, the statement P is equal to NP is known to have a vast kingdom. In this video, we will look at the kingdom of the brute. What will happen if there exists a quantum brute force algorithm for finding passwords more efficiently than Grover's algorithm? To recap, we are analyzing the task of finding the password to a file, and we know the operations that are involved in checking a password. However, figuring out the password by analyzing the operations is too hard for us, so we want to find the password just by trying out various passwords in the password checker. We had a trillion possible passwords, and we reasoned that you need to make nearly a trillion guesses to find the password, and that is too costly. But then we saw that if you use quantum computing, you can do better. We saw some simple quantum algorithms, and I claimed that Grover's algorithm can do this with at most 800 billion uses of the quantum password checker. But can that be brought down to just a billion, a million, 1,000? Let's consider the possibility that it can be done in a billion guesses. Let's give this possibility a name. Let's call it Super Grover. We'll need to recall a bit about what quantum brute force algorithms are like in order to analyze Super Grover. The memory of a normal computer can be specified by specifying the memory setting, that is the value of each variable. A quantum computer's memory can be in a superposition of multiple memory settings. To perform an operation on our memory, we specify what each memory setting should become. For instance, here's an example quantum operation. And what the quantum operation does to its memory is to just do the operation on each memory setting and add up the resulting superpositions. Although the calculations might look messy, the rules are really simple, and you can ignore the calculations here. There were some further constraints on what operations are actually allowed by quantum mechanics, but they are not important to this video, so I won't recap them. The last thing we have to recap is what the quantum password checking operation is like. And this was really simple. It just looked at the guess variable of a memory setting and multiplies that setting with -1 if the guess was the correct password, and returns the original memory setting otherwise. Okay, recap done. Let's now take a look at Super Grover's kingdom. What's amazing about how these kingdoms grow is how they sometimes rope in subjects from seemingly unrelated fields of mathematics. We're going to do that now by viewing quantum brute force algorithms from a slightly different perspective. Here's an example algorithm we had looked at. It had an initial memory, and then we passed it through a password checker. To know the memory after it had gone through the password checker, we looked at the 4 possibilities of which passwords are valid. We calculated what happens in each case, and then did 4 calculations again when we performed the new quantum operation. This time around, we'll treat the passwords as unknown, and we'll see that this more informatively captures how the superposition depends on the valid passwords. This works particularly well if we define the unknowns x1, which is 0 if password 1 is not the correct password, and 1 if password 1 is the correct password. Similarly, define x2, which is 0 if password 2 is not the correct password, and 1 if password 2 is the correct password. Equipped with x1 and x2, let's see what the password checker does. If the guess is password 1, then the password checker attaches the amplitude 1 minus 2x1 to it. It might look like I'm suddenly changing the password checker, but think about it. If password 1 is correct, then x1 is 1, and so the amplitude we're attaching is minus 1. If password 1 is wrong, then x1 is 0, and so the amplitude is 1. This is exactly the same password checker. It's just written with variables now. Similarly, the guess 2 gets the amplitude 1 minus 2x2. We specified the behavior of the password checker, and we didn't even have to split it into cases. So now we can redo our calculations in the algorithm. The superposition after the first password checker is just the memory setting 1 with amplitude 1 minus 2x1 by square root 2, and the memory setting 2 with amplitude 1 minus 2x2 by square root 2. You can check it against the cases we had individually computed earlier. Our next step was to do the new quantum operation shown here. When we do the operation, each memory setting changes accordingly, and we then add up the superpositions to get the final superposition. And this is it. Now when we look at this final state, we know the probability of seeing 1 and the probability of seeing 2. It's just the square of their amplitudes. The probability of seeing 1 is 1 minus x1 minus x2 squared. If none of the passwords are valid, that's 1 minus 0 squared, so with probability 1 we will see the value 1. If exactly one of the passwords are valid, we would see it with probability 1 minus 1 squared, so we will always see the value 2 instead. And if somehow both passwords were valid, we would again see the value 1, because we'd see that with probability 1 minus 2 squared, which is 1. So with this one expression, we were able to fully analyze all the cases. At the same time, we have made a connection between quantum algorithms and a certain type of polynomials where there's more than one variable, called multivariate polynomials. Let's use the same logic for any quantum algorithm. We start with some superposition. All its amplitudes are just plain numbers. When we pass it through the password checker, the amplitudes now get multiplied by something of the form 1 minus 2xi. So the amplitudes are now degree 1 polynomials. Then we do some other operation. To calculate the new amplitudes, we see that we're just multiplying our earlier amplitudes by numbers and then adding them up. This doesn't change the degree of the amplitudes, it just mixes them together. Now if you pass it through the password checker again, the amplitudes again get multiplied by things of the form 1 minus 2xi. Now the amplitudes become degree 2. Another operation will create superpositions and add them up, so they will still be degree 2 polynomials. Then if we pass it through another password checker, they become degree 3 polynomials, and so it continues. So if we run SuperGrover, our final state can be represented by a superposition where the amplitudes are multivariate polynomials of degree 1 billion. At this point, we look at the superposition, and based on the memory state that we see, we should be able to tell what the password was. The probability that we see a particular memory state is now a degree billion polynomial squared. When we square a polynomial, its degree doubles, so that's a polynomial of degree 2 billion. Now there would be some memory settings for which SuperGrover would have said that the password is 1. We can find out the probability that SuperGrover says the password is 1 by summing the probabilities corresponding to those memory settings. Let's call this resultant polynomial P1 of x1, x2, and so on. For short, we'll just call it P1 without mentioning the variables every time. P1 also has degree 2 billion. We can also find the polynomial P2, which is the probability that SuperGrover says that the correct password is password number 2. And we can calculate P3, P4, and so on till P trillion. Since we're assuming that SuperGrover does actually find the correct password, here is what we know about the polynomials. If we evaluate P1 with x1 equals to 1 and all other x's equals to 0, then the answer should be really close to 1. Since if 1 is the only valid password, then SuperGrover should have a high probability of saying that password 1 is the correct password. If we evaluate P1 with x2 equals to 1 and all other x's equal to 0, then the answer should be really close to 0, since SuperGrover should not be answering that password 1 is the correct answer. We can make similar statements about P2, P3, and all the other polynomials. Now we have a trillion polynomials. That's too much. Let's change that to just one polynomial. Here's a new polynomial, PSG, where the SG stands for SuperGrover. It is defined as PSG is equal to x1 times p1 plus x2 times p2 plus x3 times p3 and so on for all the trillion terms. The degree of PSG has increased by 1 and is now 2 billion plus 1 because we've multiplied a variable with each p. Let's now see some beautiful properties of this polynomial. If PSG gets input x1 equal to 0, x2 equal to 0, and all x is equal to 0, then since each term in the addition has an x variable multiplied, they will all become 0. If PSG gets input with only x1 equals to 1, then all the other terms will become 0 and the output will be the same as the output of P1. We know P1 is close to 1 when x1 is 1 and all other x's are 0. So PSG is also close to 1. This same logic works for any input where exactly one of the x's is 1. Only one term will not be 0, and that one will be close to 1. There's one more property that PSG has. No matter which x's I set to 0 and which I set to 1, the value of PSG is always between 0 and 1. For instance, let's take the case when only x1 and x2 are 1. Then this is the same as P1 plus P2 since all the other terms are 0. P1 will give you the probability that SuperGrover outputs 1 when 1 and 2 are the valid passwords. Similarly, P2 is the probability that SuperGrover will output 2 when 1 and 2 are the valid passwords. So P1 plus P2 is the probability that SuperGrover outputs 1 or 2 when 1 and 2 are the valid passwords. Since it's a probability, it must lie between 0 and 1. A polynomial with these three properties is a really nicely structured polynomial. We don't know if there is a polynomial satisfying properties A, B, and C with degree at most 2 billion plus 1. If SuperGrover actually exists, then we can get from it the polynomial PSG, which would satisfy all these properties. So such a nice structured polynomial takes up an important residence in SuperGrover's kingdom. However, multivariate polynomials are quite tough to imagine. It would be nicer if we had a polynomial with just one variable that had some nice structure. And we can actually find such a polynomial using something called symmetrization. I'll show this by an example. Here is a multivariate polynomial. It doesn't have any x1 squared term or similar term with exponents. But that's because if x1 is only taking values 0 or 1, x1 squared is the same as x1. So from now on, all polynomials won't have exponents. This polynomial in particular takes the value 0 when all x's are 0. It takes a value close to 1 when exactly one of them is 1, and it is still between 0 and 1 on all other values as well. It's not the best polynomial like this, but I'm taking it to show how symmetrization works. If I change the role of x1 and x2, I get this new polynomial. All the nice properties remain. This is because the properties are symmetric. They treat each x the same. So in particular, if I do all possible interchanging of variables and I get all those different polynomials and I take their average, I should get a new polynomial which I'll call P symmetric. And it will also have the same properties. It should still be 0 when all x's are 0 because each of the polynomials were 0 and we're taking their average. Now if I set x1 to 1, it should still be close to 1 because all the polynomials would have been close to 1. And for any value of x, P symmetric should be between 0 and 1, again because all the polynomials were. So why is this P symmetric more interesting? It's because the coefficients of x1, x2, and x1, x3, and x2, x3 should all be the same. Think about it, the coefficient of x1, x2 in P symmetric comes from averaging all the polynomials with all the variables switched around. So the coefficient of x1, x2 in P symmetric should be the average of the coefficients of x1, x2, x1, x3, and x2, x3 in P. And same for x1, x3, and x2, x3. Similarly, the coefficients of x1, of x2, and of x3 in P symmetric will all be the average of their coefficients in P. Now that we have such a neat polynomial, we do one last trick. x1 plus x2 plus x3 to the power 3 is just 6x1, x2, x3 plus 6x1, x2 plus 6x1, x3 and so on. x1 plus x2 plus x3 squared is 2x1, x2 plus 2x1, x3 plus 2x2, x3 plus x1 plus x2 plus x3. So x1 plus x2 plus x3 cubed divided by 4 would be as shown here. We've gotten the degree 3 term the same as p-symmetric. To get the degree 2 term the same, we add an appropriate amount of x1 plus x2 plus x3 squared. The coefficients of the linear term won't match, but we can add an appropriate amount of x1 plus x2 plus x3. This is what symmetrization is. Given a structured multivariate polynomial like we had, it's a way to come up with another multivariate polynomial with the same structure, but that is essentially univariate. Essentially univariate because it's really just the polynomial 0.25x cubed minus 1.475x squared plus 2.175x, which we'll call u, applied to the input x1 plus x2 plus x3. We can find the value of u of 0 by setting all xi's to be 0. We can find u of 1 by setting exactly one of the xi's to 1, u of 2 by setting two xi's to 1, and u of 3 by setting all xi's to 1. So u of 0 is 0, u of 1 is close to 1, and u of 2 and u of 3 are both between 0 and 1, because they are the values of p-symmetric when 2 and 3 of the x's are set to 1 respectively. This polynomial u is also really beautiful. It takes center place in the kingdom of Supergrover, a univariate polynomial of degree 2 billion plus 1 that evaluates to 0 on input 0, evaluates near 1 on input 1, and evaluates between 0 and 1 on inputs 2, 3, 4, 5, and so on till trillion. Unfortunately for Supergrover, its kingdom is starting to trespass into an already conquered region. Let's take another look at it. A univariate polynomial of degree 2 billion plus 1 that evaluates to 0 on input 0, evaluates near 1 on input 1, and evaluates between 0 and 1 on inputs 2, 3, and so on till trillion. You see, this polynomial u very quickly goes from 0 to near 1, and then stays between 0 and 1 for a long time, as if it were in one of the arenas from the series on Markov's theorem. Indeed, let's take this polynomial u and do some simple operations on it, scaling it, squeezing it, and shifting it, so that it actually fits the arena. The length of the arena has changed from a trillion to 2, so the intervals are now of size 2 by trillion. Now we know it takes value minus 1 at x equals to minus 1, goes near 1 at x equal to minus 1 plus 2 divided by trillion, and stays between minus 1 and 1 at x values of minus 1 plus 4 divided by trillion, minus 1 plus 6 divided by trillion, and so on till 1. None of these modifications changes its degree, but it might not actually fit the arena yet. We know that at regular intervals it is between minus 1 and 1, but maybe between these intervals it goes outside the arena, perhaps reaching a value of say 1.1. So let's expand the arena so that it fits.
Hello? Oops, I did not mean to interrupt. Let me move out of the way. I am the chef. I was called here.
Oh, hi, chef. We were just looking at this miraculous 2 billion plus 1 degree polynomial that stays in the arena here. It has a really large slope at the left side of the arena.
Oh, is that so? Let me fit myself in the arena and stretch so that I also fit exactly in this arena. So, how much slope does your polynomial have?
Well, since the intervals are of width 2 by trillion, and it goes from near minus 1 to near 1 in one interval, it has to have a slope of at least a trillion by 2.
But that's impossible. A chef of degree 2 billion plus 1 would have the maximum slope in the normal arena, where it has a slope of around 4 billion. In this enlarged arena, it would be the same chef enlarged which has the maximum slope. So that's a slope of around 4.4 billion, much smaller than trillion by 2. Your polynomial must have degree larger than 600 billion in order to do what you claim.
Maybe we got the arena wrong. Maybe it goes really far outside the arena in between the intervals.
That's not possible either. Even if your polynomial goes to 1.1, that means it must have a slope of a trillion divided by 10 between the intervals, just to be able to touch 1.1 and come back to 1 in an interval of size 2 divided by trillion. You can do the maths assuming it goes far outside, and you'll see that you hit the same issue. That's too large a slope for such a small degree polynomial.
And so the special polynomial u cannot exist. But the polynomial u was part of Super Grover's kingdom. If Super Grover ever becomes reality, the polynomial u must become reality. So the chef didn't just stop the polynomial u, it stopped Super Grover itself from ever becoming reality. It doesn't matter how smart the mathematicians are, they can never make a brute force quantum algorithm that finds a password among trillion passwords with just a billion uses of the password checker. Or if we calculate it more carefully, even with 300 billion uses of the password checker. Chef just saved society.